So now let's look at evaluating a limit by using Taylor series. Here we have a limit as x approaches 0 of sine x minus tan inverse x over x cubed. If we think about the form here, that's going to 0, that's going to 0, that's going to 0. So we have 0 over 0 situation. It's an indeterminate form. We could try L'Hopital's rule, but this one works out quite nicely if we replace these two transcendental functions by their Taylor series. First of all, we know already we proved sine x equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial and so on. And I've mentioned a couple of times that the big three we'll be using are e to the x, sine x, and cosine x. You should know those series. But occasionally in the homework, we'll work with some other functions. And in the book, there's a little table of Taylor series. So I don't expect you to derive that every time. For the homework, just look it up in the table. If I asked you this problem on a quiz or test, I would provide you with the series for tan inverse. I don't expect you to have that one memorized. Just make sure you know e to the x, sine x, and cosine x. So tan inverse, if you look in that table, looks actually a lot like sine, except instead of those being factorials, it's just that n there. And this is actually only good. You know, what was nice is sine, cosine, e to the x, those were equal to their Taylor series everywhere. Tan inverse is actually defined everywhere, but it's not equal to its Taylor series everywhere. If you look in that table, it's for all x less than 1 in absolute value. Actually, it's less than or equal. But that's neither here nor there. We are trying to head towards 0. So in the neighborhood around 0, where we're interested in, this is equal. OK, so what I want to do is write this expression now by replacing those guys with their series. And I know it's equal. This is not an approximation. Sine equals that. Tan inverse equals that, so long as we're in that interval, which we are. So, and I think when you're working these, I would work with just writing out some terms and using the ellipsis, because sigma notation can sometimes be difficult to think about when you're trying to see how these two interact with each other. So minus tan inverse is x minus x cubed over 3 plus x to the 5th over 5, and so on, all over x cubed. Now let's just go through and see how these guys cancel. I've got x minus x, so the first degree term is gone. Then I've got negative x cubed over 6 minus a minus, so plus x cubed over 3. That's my x cubed term. Then my x to the 5th over 5 factorial minus x to the 5th over 5, and so on. Now, I want to cancel here. Notice that the lowest degree term here is x cubed. I could cancel x cubed through every one of these. It's going to lower all those by 3 degrees. And that's why series work really nice here, because once I do that, this becomes negative a 6th plus a 3rd plus x x squared over 5 factorial minus x squared over 5, and so on. Oh yeah, and actually that canceled. I didn't have to write a fraction. I'll just write that as 1. Okay, notice now, as x goes to 0, all these other terms, there's going to be an x squared term, an x to the 4th, an x to the 6th, an x to the 8th, but those are all headed to 0. The only thing we're left with is this constant up front. So we get a limit of 1/6. No approximating at all, right? What made this work out nicely for us is that once we combined up these two series, we got something that then we could cancel this x cubed, right? Here, these are non-polynomials, so there's nothing I can do to simplify. But once these are written as polynomials, I can then reduce with that x cubed. And once I've done that, all these higher degree terms are all headed to 0, and all we're left with is that constant. Now, it really depends on the setup whether Taylor series will do us any good. This happened to work out really nice. Notice what made it work so nice is that when you subtract these two, the first degree term canceled. And so that lowest one was a third degree term, which made this a constant. So these have to be somewhat contrived to work out nicely. But it is another option in your toolkit of ways to evaluate limits, is to look at the Taylor series instead.